last speaker will be Christian Dahmen, who graduated with a degree in electrical engineering from Cologne University of Applied Science in Germany, and his focus was on optical and biomedical technologies. He's now a research associate with the Division of Microrobotics and Control Engineering and head of the group called Vision Feedback for Micro and Nano Handling. His topic will be magnetic resonance imaging of magnetic nanobots for targeted drug delivery. Dr. Dahmen.
Thank you for the warm introduction. First of all, I want to thank Dr. Rosenblatt for giving the great opportunity to present here in this collection of really excellent and great people. And also a special thanks to Temple and Genesis, who did a really excellent job on organizing this whole stuff. I think probably you have been thanked in every way possible already, so I will leave it like that. So, where is this? Here. What was it? Next. Okay. Okay, so, my title is Magnetic Resonance Imaging of Magnetic Nanobots for Targeted Drug Delivery. And I will give a first structure in the beginning. That means I will give a short introduction about what is the goal of this whole approach, what we are following. I will say something to the principle, what we're exploiting of MRI magnetic targeting. I will present some experiments, what we did about imaging, then the results, the MRI artifacts, which are produced from the magnetic particles. I will say something to the image processing, what we use, summarize and give some acknowledgements. And before I go on now like that, I would like to direct your attention to the abstract booklet, what probably every one of you has, because it's like a good picture of the vision, perhaps, where nanobots perhaps are going to. You can see they are like flowing in the bloodstream, they have actuators, they perhaps grip something, they are trying to influence our health or whatever, trying to kill some bad bacteria or cancer cells or whatever. So the thing about this is, if you look at them, they have to move, they have to have energy, and they have to be controlled. So that leaves us with the problem how we do that. If we have some untethered devices, especially if they are very small, we have the problem that they need energy supply. Implants, we can perhaps put batteries, but it has drawbacks, of course. So then we need them to be controlled. If we put an implant just anywhere in the body and it's fixed, we don't care about that. But if we want to move them around, to have them to be dynamically assigned perhaps to some region in the body to do some functions, to kill cancer cells, kill tumors, whatever, then we have to control the movement. And in order to control the movement, we have to have also sensory feedback. That means these small nanobots have to somehow feel or see whatever to be able to react. And of course, somewhere should be some kind of intelligence to control them. So the possible solutions, which is like lies near, is to use an external energy supply, in this case wireless, to use external wireless movement control, and to use external sensor feedback. So that leaves the nanobots to be the most simple possible nanobot, just without intelligence, without like own movement control, whatever, sensory feedback. And the best case in that is, why not use technologies which exist already in in the clinic. So that leaves us with that we want to use the MRI for this. One thing about the MRI is the MRI uses magnetic gradient fields for imaging purposes. So what is special about gradients, magnetic gradients, is that a ferromagnetic object which is in a gradient field has a force exerted on it. So that means if we use the gradients and we design the gradients in that way, that in a special way, then we are able to push these particles or these nanobots or whatever we want to move. So, and that is the basic principle of this. And the feasibility of this has been shown already by a group here, not far from here in Montreal, Professor Martel, which has shown that in principle you can move things in the MRI. And I think the use of this approach to enable new therapies, or to improve existing therapies, to use this principle of moving with magnetic gradient fields, which the MRI anyway can produce, looks very promising. So, and the principle, what we think is like that. We take magnetic particles, which are functionalized and perhaps loaded with drugs like chemotherapeuticums or something like that. We introduce them into the body at a place where it's somehow suitable. And then we use the gradient fields to enable propulsion. That means the magnetic object, this particle which is augmented with a ferromagnetic material or whatever, it will follow the magnetic gradient, which means it's by physics trying to minimize its energy. And the direction of the gradient determines the movement of the particle. So that means if we modulate the gradient fields, we can control the particle. So, and in this case here, you can see like a scheme of how it could be. We have a vessel, and the red dots depict the positions where the particles would be after a certain time. It would start on the bottom. It would go through the vessel, and we would control it to take the branch what we want it to take. So, and the MR imaging, in this case, delivers us the position information so that we have a complete control loop. The positive side about this is that the only components what we need when it's finished is a standard MRI scanner, which is in most clinics, I think there is one. Then we need the magnetic particles or the objects, whatever we want to move. And then the rest what we need is just software. That means we need image processing to find out where the particles are and where they move. Then we need a controller which determines where we want to move and what steps we have to take to do that. And then we have to have a gradient controller which designs and like chooses the gradients which are needed to fulfill this goal. So the thing is, what I forgot before, the nanoparticles or the nanobots what we are using, I mean, they are relatively simple. And there are two approaches which may be followed. The first one is here on the bottom. It's nanoparticles, like real filled with chemotherapeutics or whatever. And the second approach, what is possible, is carbon nanotubes, also functionalized, perhaps filled with something, and with attached ferromagnetic core. Oh. So, and the overall like control loop, what we generate then, is depicted here. So we have, which one was it? Ah, here. So we have here the magnetic object, and this magnetic object leads to a distortion in the magnetic field. That means the signal what we receive is different than when the magnetic object is not there. So after the image reconstruction, we will see some kind of artifacts in the image. And we are able to use image processing means to detect that and to determine the position. The position is then fed into a movement controller, which then takes the necessary steps to move it in the position where we want. And that means the movement controller gives commands to the gradient controller, which then generates the necessary imaging and propulsion gradients, which are put on the gradient coils and then lead to either imaging field or a magnetic force which is exerted on the object, what we want to move. One thing what is important about that is that the MRI is using the gradient fields also for imaging purposes. That means we cannot do both at the same time, because we're like abusing the MRI technology for doing something what it was not designed for. That means we have to do kind of time slicing. We have some imaging phase with normal sequences used for imaging, or perhaps specifically designed sequences where the gradients are used for that. And then we have a propulsion phase where we use specifically designed gradients to propel the object. So, yes, so we did some experiments about that using, well, not nano scale parts yet. I think if we go with this exponential model, we are still in the phase where you can consider the work going on linearly, but I hope we'll be in the exponential phase soon, and like it will go faster. Actually, this project is relatively fresh, so we used different objects in different sizes. That means one 3 × 1 × 1 millimeter cylinder, a 2 millimeter × 1 × 1 cylinder, a 1 millimeter cube, and a half cube. And the material used was ST51 steel, which is just structural steel, German naming for that. So, and here we see the different objects depicted. So, after putting that into the MRI, where most MRI controllers are not very happy about, I mean, normally they avoid putting ferromagnetic materials inside, because if it's too big, you don't get it out anymore. Probably someone of you have seen these images of some chairs or whatever gluing at the MRI, and then you have to turn it off to get it out. So we had some discussions about that and everything. So, and finally we were able to put it inside. And for that we filled single particles into 100 milliliter polyethylene bottles. The diameter of these bottles is 48 millimeters. As I said, a single particle per bottle, centered in the middle, surrounded by agar gel. So, and the scans, what I'm showing now, have been executed at the Cyclotron Research Center at the University of Liège in Belgium on a Siemens Medical Solutions Allegra 3 Tesla system. So here we have a localizer scan of the first particle, which is the biggest one. And what we can see here is this shape of the bottle. This is the top view. This is one side view. This is the other side view. And if we would put just the agar, then this block would be white. So, and here we see these dark spots, this artifact that is the distortion of the field, which, well, is quite impressive, because the dimension of this, the diameter of this is 48 millimeters. The object is like 1 × 3 millimeters. So that means the artifact spans much wider, much further than the object itself is. So we repeated that with the different other particles. Here we took a smaller one, not half, 2/3 of the volume, if you say it like that. So, and we see the artifact is not getting considerably smaller in this case. And with the next cube, the same. It's still quite expressed here. And with the smallest one, when we take the half cube, then we see a considerable decrease in the size of this artifact. But this particle, what we have here, is below the resolution of the MRI. So that means it's still quite big. So then we need some more scans. Here we have gradient echo scans. This is now a time series, not a time series, it's a slice series. That means it is slicing through the bottle from bottom to top. And perhaps you can see that this one has the least expressed this artifact, and this one has the biggest. But it's everything quite big. So, and we did a second scan with spin echo sequences, and this really looks very fascinating. I don't know really, we didn't look into that yet, why it looks so funny, but here you can see that it spans even, like the artifact is not only like around the object, but it can be completely somewhere else also. So, and so the goal is to use image processing to detect these particles. What we need is, in order to control everything, we need relatively fast feedback. That means, first of all, the sequences which we use for imaging have to be fast. Second, we are limited in the choice of algorithms. And well, to prototype that, we are using own developed generic image stream processing software, where we can take algorithms, implement algorithms, combine them with each other, and then process live image data just to try everything. This is very flexible software it got. We originally have that from the micro-robotics. So here is just a picture showing how it is built, like an interface to the image generation device. Then we have the algorithms, and then some kind of output handlers which write it to disk, write it to the screen, write it to some transfer data to some servers or whatever. And the functions, what we have to do here is, first we have to recognize the particles, and second we have to track them after we recognize them. So that means overall the imaging system looks like that. This is now the block what was the image processing part in the other diagram showed before. So we have an MRI interface. We generate an image. We do some pre-processing. Then we recognize the particles, give that information on the screen and on to the controller. And when we recognize the particle, we trigger the tracking algorithm and initialize it, which will from then deliver the position data with each frame to the controller. And of course, it will update the scanning parameters so that the scan will follow also the object. So, and then I will conclude. First of all, what is clear from the beginning, the principle has been shown already and it works. That has been done by Professor Martel and his group. We can use the MRI to detect particles which are much smaller. I mean, these are still quite big particles. I mean, they are not like nanoparticles or something. So, but it means that we can detect particles which are much smaller than the resolution of the MRI, which gives us like some advantage to follow even smaller particles. And what we still have to look at, first of all, different sequences, different like imaging parameters, And we have to look if we can detect these particles and we can see them, the artifacts, in real tissue, because real tissue is still different from agar gel. And of course, many different problems, and any problems considering the imaging, the control, and the particle design have to be overcome still. But in my opinion, the possibilities which we will have from a system doing this are really promising. So I'll just give acknowledgements. This has been funded by the European Commission, and the project acronym is NANOMA. So, do you have any questions?
Are there some questions?
Yeah, it's late.
There are a lot of iron-containing molecules in the body.
Mm-hmm.
Hemoglobin and many enzymes have iron.
Mm-hmm.
And these, I think the resident bacteria probably have magnetite.
Mm-hmm.
Has there any opportunity to think about those issues or do something?
What do you mean, those issues? Like to...
I mean, they're in a magnetic flux, I take it, isn't that?
Yeah, but I mean, the cells, if you put someone in the MRI scanner, I mean, anyway, they are like in the magnetic field. So, I mean, it's not different. It will not be different from scanning someone, in a way, because we will still obey the limits what are made by the FDA and by the regulators.
So this would be a short period of
yeah,
MRI.
yeah. I mean, short period, not necessarily. Maybe half an hour. Maybe depends on like how complex the problem is, but reasonable, I would say.
Are there further questions? If not, I'd like to thank you for giving an excellent talk to
Thank you.
finish this project.